In this video, we're going to cover the fundamentals of probability, but beforehand, we're going to address some student questions around circular functions. Enjoy. Let's make a start. So, the question you've submitted is, how do we do sketching, essentially? So how do we sketch this type of circular function? 3a, 3b. So 3a, I'm assuming that one isn't probably too bad for you. What do you do in 3a there?
Just sub in the values.
Yeah, precisely. So sine 2 bracket x minus pi on 3. To get those, you would just sub in f at 0, x equals 0 and x equals 2 pi. There's nothing too crazy going on there. So for the more complicated bit will be the actual sketch overall of f. So how much of sketching circular functions do you remember? How might we start this out?
I know we need to calculate the period and the altitude.
Yep, period and amplitude for sure. So period, how do we calculate period?
2 pi over n.
Yeah. And what's our n value in this case?
Would it be 1?
So the n is going to be that there. So whenever you have a circular function, you have something like f of x equals a sine bracket n bracket x take h plus k, maybe plus c. So the n value is always the coefficient on the x. Whether or not it's been factorized out is sort of whatever. So in this case, n is 2, capital T is pi, or period is pi. Okay? From there, amplitude. Well, amplitude is always the thing at the front here, so that's 1. So as far as peak and trough goes, what are those going to be?
I'm not sure what that means, peak.
Yep, so like a circular function looks something like that. This is a peak, this is a trough. So the amplitude allows you to solve, or at least find the y values there. Any ideas what we could do there?
Not really.
Not really, that's okay. How about you, Sanjay? Any thoughts?
Um, mm, well, wouldn't the peak just be +2 and then the trough be -2? Because there's no dilation, up or down. I mean, translation, sorry.
Yeah, there's no translation up or down. So
Yeah.
you got the right idea in the sense they should both be the same value. But the thing is,
Oh,
they won't.
no, it's a +1 and -1, sorry.
Yeah. So it's whatever the a value is the plus minus. So peak will be at +1, trough will be at -1. So if we were to start drawing that on this graph, you'd have like a 1 here, you'd have like a -1 there. Now this isn't exactly what we're drawing, this is just a demonstration of what that might start to look like, but yeah. So peaks will be the positive version, troughs will be the negative version, or at least the bigger and smaller versions. Cool so far?
Yeah.
So when it comes to circular functions, what we essentially have are a few key features to watch out for. So we've got mid-levels, so that's all of these, the middle lines, and we've got peaks and we've got troughs. Within any given period of a circular function, there's going to be 5 key features. So if this was like 0 to pi, for example, then what we find is the easiest way to go about finding the x location for each of these spots is to start with the period, halve it to get the middle spot, halve it again to get this spot, and then fill in the remaining blank to get the final spot. And this will by default be 0 if there's no like horizontal translations or anything like that. So that's how you begin to do that, at least start sketching those out. But when you have a horizontal translation, like we do here, this x equal the minus pi over 3, it means taking what we have here and shifting all of this to the right by pi over 3. So what we now end up with is still going to have our peak of 1, our trough of -1, but instead of starting at 0, it's going to start at pi over 3. The next key feature is going to be pi over 4 plus pi over 3. The next is pi over 2 plus pi over 3. And so that's a bit nasty to try and all do in your head. So I'd recommend just sort of going to the side and being like, okay, so I used to be at pi over 4, now I'm adding pi over 3. Well, that's the same thing as doing the cross multiply. So 3 pi plus 4 pi over 12, 4, 5, 6, 7 pi on 12. So that next spot down here, 7 pi on 12. Then again, next one over, pi over 2, pi over 2 plus pi over 3. So 3 pi plus 2 pi over 6, 5 pi on 6. So that's the next one. Rinse, repeat until you do the entire, all 5 sections. But 3 of them, there's only a couple more. 3 pi over 4. 3 pi over 4 plus pi over 3. So that's 9, 4, 12, 13 pi on 4. 13 pi on 4. Ideally, you'd have them all equidistant. My spacing's a little bit off. And then pi plus pi over 3. That was not too hard to remember. That should just be 4 pi over 3. Or at least not too hard to do in your head. Watch that be the one I get wrong. But anyway, from there, all you're doing is now translating, it starts at a, well, that was actually an example. Maybe I should double check. We have positive sign, so yeah, this should be the overall curve. So positive sign means it starts at a 0. So it's going to start here. It's going to go to a peak immediately after. Bang, bang, bang. And then you just draw your curve connecting all those points. And if you've separated them nicely, you'll get a nice curve. Otherwise, you'll get something like what I've just drawn there. But that is to draw the initial curve. What we have to do is consider that we're only sketching this from 0 to 2 pi. So the question was saying we actually only wanted 0 to 2 pi. So what we have to consider here is a cutoff point. Now, this one's exceptionally nasty because it goes for more than one cycle. So 4 pi over 3 is still less than 2 pi. We have to keep going, essentially. What that ends up meaning is repeatedly doing what I was doing over here, which was adding the pi over 3s to the points, and you would just keep doing that until you exceed your 2 pi. As soon as you exceed it, you cut off and you leave it there. To go backwards to 0, that one's not so bad because when you subtract pi over 3 again, the next well, hang on, the quarter period is no. Yeah, pi over 4 goes backwards. So you repeatedly, yeah, I described that wrong. Rather than adding pi over 3 to all of these to continue on, you're adding pi over 4 to all of them. That's my bad. I already had all these as pi over 4 separated, so that's why it didn't matter here. You were just shifting everything right by pi over 3. But if you want to continue this pattern, you are adding pi over 4s from there. Was that clear enough, the explanation there? I have to walk that one back a bit. Does it make sense why it's pi over 4 that we should be adding to all these and not pi over 3?
I don't really get it because, yeah, I don't really get it.
Yeah, okay. Basically, what we're trying to achieve is finding all the key features of our peaks, troughs, middles, that sort of thing. And we know that they always occur at quarter periods from each other. And so, in the absence of any horizontal translations, you normally start at 0, end at the period, and then like do your quarter up to get all these key features. Is that bit fine?
Yeah.
Okay. So maybe instead of doing what I've just done, which is start with one cycle and go forward, maybe it's better to sketch this from 0 to 2 pi and then add the pi over 3 later. Because getting from here to here is just taking what we had before and applying our shift of pi over 3 to all these. So maybe it'd be easier for you to extend this out to 2 pi, and so you'd repeatedly add your pi over 4s. So it's going to be that, like that, like that. So 4 pi over 4, 5 pi over 4. Let's get rid of that. 6 pi over 4, 7 pi over 4, and 8 pi over 4. So this is 3 pi on 2. Is it fair enough how I've extended that out?
Yeah.
Okay. So we're just going to continue our graph. So this should be a peak, this should be a middle, this should be a trough, and then this should be a middle. So once you have that between 0 and 2 pi, which is the whole domain there, you're just going to take this graph and then shift it right by pi over 3, which means taking all of these coordinates that we just found and adding pi over 3 to them all. It's nasty, but that is the game. So kind of like what I was doing here, which was 0 plus pi over 3 gets hit at pi over 3. Pi over 4 plus pi over 3 gets hit at there. So on, so forth, so on, so forth. You would just repeatedly do that to get to the end there. Fair enough?
Yep.
Cool. So that's going to get you... Well, let's try and continue with that. Okay. So that's one cycle. We now need... How many more points were there? 1, 2, 3, 4 more points. 1, 2, 3, 4. And we ended at pi last time. Pi plus pi over 3 was 4 pi over 3. This plus pi over 3. This plus pi over 3. This. Now, I'm just going to do the CAS at this point because that's a lot of handwriting for nothing. Oh, there we go. Another flaw of this is I can't record my CAS if I'm doing... Okay, that's fine. Take my word for it that we're going to be using CAS to finish up some of these. So we had 5 pi on 4 plus pi on 3. That's going to give us 19 pi on 12 for the next one. Pi on 12. Adding another pi on 3 is going to get us to 23 pi on 12. Doing it again is going to get us to 9 pi on 4. And at this point we would actually stop because 9 pi over 4 is bigger than 2 pi. We don't want to exceed that. And so we can safely cut that. Cut this off here at 2 pi, which is what we need to stop. And we can leave that there for a little bit, just so you can dot the rest of it out. But reminder that you'll have to rub it out afterwards. So we ended up with a mid, peak, mid, and this would be a trough, but we didn't quite get there. So it's got to stop early at this spot here. And then we can now get rid of that point because we've got our rough sketch there. Okay? Now that's almost everything. Only thing now is we've got to find out what happens at 0, which would have been solved in 3a. So f of 0 and f of 2 pi, those should be the same thing. So if I were to do f of 0, it would be subbing in a 0 here. So sine of 2, 0 minus pi on 3. It's the same thing as sine of negative 2 pi on 3. On the unit circle, negative 2 pi over 3 is down there, which is going to mean we're going to have, well, it's a bit steeper, really. But that spot's going to be negative root 3 on 2. So when we continue this curve, it's going to cut here at minus root 3 on 2. And 2 pi will be the same thing because it's periodic. So this will be 2 pi, comma, minus root 3 on 2. Nasty question. In an exam, you'll only ever have to do one cycle. We've had to do 2 cycles and fix things up. So really they're just sort of going above and beyond to try and really stress test how much you're able to sketch here. Is it fair enough how we ended up here?
Yep. Thank you.
Yep.
Cool. Okay. In a real exam, you'd be cut off here. And that's all you'd have to do. But okay, that's that one. Let's change over the screen share to the actual curriculum content now, which is looking at some probability stuff this time. So, okay, got that going. Nice. So, starting to look at probability. What we're essentially doing here is looking at the fundamentals. You've probably seen a decent amount of the fundamentals at this point. First of which being, simply put, you can find the probability of any event occurring by figuring out how many times does the event you care about occur, and then divide by the total number of possible events. That's all this is explaining here. So if I had a 6-sided die, I have the possibilities of numbers 1 through 6. If I want to find the probability of, say, rolling a 6, there's only one possibility of that occurring, 6 total possibilities, 1 out of 6 chance of rolling that dice, rolling that 6 rather. So nothing too crazy there. I've got a whole bunch of different examples here, showing you the sample spaces for each of them and the potential probabilities that could be asked. So there'll be certain things. You just start by figuring out what are the possible outcomes. You can't see the screen share. Yeah, there should be another screen share for the notes. If you click on, I've got 2 accounts on here. One is for screen sharing the handwritten bit, and another for screen sharing the notes.
It's not sharing though, like we can't see it.
Oh. It says it on mine. Have you clicked out of, you know what, I'll just kill this one. Maybe you'll see the other one after I kill it. If I kill that one, did the other one show up?
Yeah, it did.
Okay. Interesting. Okay. Anyway, so all I was showing was this, right? 6-sided die. If you wanted to roll a 6, 1 out of 6 chance. I've got a few other examples here. Different sample spaces. Do I need to go into any more detail on those, or is it fair enough what I'm talking about?
Fair enough.
Cool. Probabilities around areas. Potentially what you could be using are area equations now. So it's like, what's the probability of hitting the red spot with a dart? Well, you just look at your total possible area that you could hit, so a rectangle in that case, and the area that you want to hit is going to be the red, so the area of the circle. So you find the circle, you find the total area, circle divided by total, that's going to be your overall probability of hitting that spot, assuming everywhere is equally likely to hit. From there, we can talk about complement probabilities. So the whole idea here is all probabilities in an experiment have to add up to 1. And so if the probability of one thing occurring is like a half, for example, then the probability of anything else occurring in that experiment needs to also be a half. It's easiest to talk about like heads and tails, for example. So only 2 outcomes of a coin toss, heads or tails. One of them is 50%, the other must therefore be 50%. If I had like, I don't know how this would work, but a weighted coin where it was more likely to hit heads, for example, like 70% heads, then the complement to that must therefore be 30%. Cool? The way that, yeah, the way that works is essentially you would denote that as A dash. So everything else except the thing is the complement probability, A dash or A prime. So if I want to find, yeah, this is actually useful for finding like ranges of numbers. So if you had to find the probability of rolling a number greater than 1 on a 6-sided die, then you could do the whole sample space thing again and say, look, okay, we have 5 total numbers out of 6, and so the probability of rolling a number greater than 1 is going to be 5 out of 6. Alternatively, and this becomes more important when you get more complicated questions, instead of doing the addition of all of these, you can just say, okay, instead of doing numbers greater than 1, I could look at all the numbers that are 1 or less and do 1 minus that, because that's the complement to that. So the alternative way of going about it is saying, okay, there's only one number that isn't greater than 1, and so if I do 1 minus the probability of that, I should also get the 5 out of 6 there. That's the gist of it, really. So those are the fundamentals there. If you have more complicated questions, so they have like multiple stages to them in a row, then doing something like a tree diagram can be kind of nice to visualize what's going on there. The standard tree diagram looks something like this. You're going to have a certain number of choices, could be 2, could be 3, depending on how complicated your question is. And essentially, the way this works is you're essentially looking at all the possibilities of the combinations of those branches. So like a very simple example, if I'm tossing a coin twice, then a tree diagram might look like this. You've got one option for heads and tails, and then after you've finished option 1, you're tossing another coin again. So heads, tails again, heads, tails again. You label all the probabilities on the branches, and that sets up your tree diagram. As far as how you use a tree diagram, it depends on what probability is being asked. So if you want to find the probability of a given outcome, so example, head, head, or what did I say? Whatever, yeah, head, head, you multiply along the branches. So you got probability head 0.5, probability head 0.5, probability of head, head 0.25. If you have more complicated examples like this, so numbers 1, 2, 3 are written on papers and you're pulling out those numbers out of a hat, it starts getting pretty big, right? This is with replacement, so the number gets put back every time. So essentially the experiment's repeating itself. You have a 1 out of 3 chance for any of the given numbers, and when you draw it twice, you're essentially doubling up what's going on there. Now that's kind of complicated. Drawing all of this would be a bit tough to do, not because it's like mentally tough, but more so it's just time consuming. So little shortcuts you can have would be like not necessarily labeling all the branches, just sort of applying it to all of them, mentally speaking, or even literally just drawing like one and then the other and then remembering, oh, okay, the rest of them have to fit out like this. Another thing you could do is instead of drawing the full tree diagram, look at the actual probability you're trying to find. In this case, what's the probability that both numbers chosen are greater than 1? Already off rip, numbers greater than 1 just means this whole section of the branch doesn't matter because that's already a number greater than 1. Then from there, you'd cut this off, you'd cut this off, and the only thing you'd have to necessarily draw would be like this. So by looking at the question ahead of time rather than just going straight for drawing the full tree diagram can really save you a lot of time for it. As far as how to calculate the probabilities afterwards, again, it's just multiplying along the branches for those particular outcomes. If you have an exceptionally large number of branches, I would just, if it's like simple enough to see what you're after, and yeah, it's the same idea. If you have an exceptionally large number of branches, just cut off the bits you care about. So if we're looking for 3 6s or 3 1s, all of this stuff doesn't matter. So you can go straight for just 1 6. Again, cut out all this stuff in the middle. You can really simplify how much you do there. Just make sure that you label the probabilities correctly. You don't forget that these are all 1 out of 6 chances, even though there's only one branch you're drawing here. It's more out of convenience rather than the fact there's only one possibility. Cool with that so far? From there is also the probability of, or possibility of getting different probabilities along the branches. So the way we handle that, or at least the kinds of questions that come across in that circumstance, is ones that are like conditional probability questions. So in this case, we have a scenario where Delaney is going to a local cafe and we're ordering either a pie or a coffee on any given day. There's going to be 2 statements in here that will tell you the probabilities with respect to each other. So the first is, if a coffee was ordered on one particular day, the probability of a coffee on the next day is 0.5. If a coffee wasn't ordered on that day, the probability of coffee on the next day is 0.8. And so what you have are 2 probabilities that are conditional on each other. If all you had was that information, you wouldn't really be able to start this question. You need a starting point. And that's what this third statement at the end is all about. On the first day of the week, Delaney orders a coffee. So you're told where to start, essentially. There's going to be some probability that's asked about it. That's sort of whatever. Again, we're doing tree diagrams here, so you can use that to your advantage to really just cut out the number of branches, but these tend not to get too big. It's usually easy enough to write out all the branches for these kinds of questions. Anyway, we're told we start with a coffee, which means at the very beginning of your tree diagram, you should have a C there, or coffee, however you want to simplify that. From there, because we started with a coffee, this statement applies. A coffee was ordered, next day coffee must therefore be 0.5. That's this bit here. Next day of a coffee, 0.5 chance. Now, we're only told the probability of this one occurring, but using our complement probabilities idea, we know that all the possible outcomes need to add up to 1. Hence, the probability of the pie, the meat pie, that's why it's M, would be 0.5 in that. 0.5, 0.5 makes 1. So that gives you branch setup number 1. These here show you what you should do in the next setup. The easiest way to go from here is to start again at C, because starting at C here is the same thing as starting at C over here. So you literally just take whatever this was and duplicate it down. If you forget that, that's fine. You can literally just do the same thing. So C, okay, that means this one applies, and then you copy and paste that down. M, a little bit different. Now we have the pie. So, or better said, doesn't order a coffee. Now this one applies. Probability of coffee on the next day is 0.8. So the C is going to get 0.8. The M is going to get 0.2 because everything has to add up to 1 there. These aren't too bad to set up. I would recommend having all of them just because it's easier to see what's going on in the full experiment. Although presumably you'd only have to have the CC and the MC branches, but it's a bit hard to selectively ignore those when you're drawing the tree diagram. The reason why we need those is because of the actual question that was asked. What is the probability of getting a coffee on the 3rd day? So we look at all our stages. Here's day 1, here's day 2, here's day 3. We want to figure out how many times do I get a, how many outcomes end up with a coffee on the third day. So we either have to get here or we have to get here. The only way you can get here is if you do CMC. The only way you get here is if you do CCC. And so this one's already a given. That's 100% chance. To get here, it's 0.5, 0.5. To get here, it's 0.5, 0.8. Add them together because probabilities multiply along the branches, but if you want to add final outcomes, or if you want to figure out the combination of final outcomes, you add those results. So 0.5, 0.8 multiplied, and then added to the 0.5, 0.5. That's how you handle those. This is a pretty repeatable setup. You'll notice by the structure of the question, without even looking into too much detail, if you see like this, then this, this, then this, like that kind of wording, it's pretty likely to be a conditional probability question that you start this one out. So that's the use of tree diagrams for multi-stage experiments. Fair enough with that? Cool. Okay. Sometimes your tree diagram isn't quite going to be enough for one reason or another. Like for example, when you have those really large sample spaces, like 2 6-sided die being rolled, that's a lot to do on a tree diagram. And so essentially what we're going to be doing now is using a two-way table or a sample space table to achieve that. So these can differ from experiment to experiment. It purely depends on what's being mentioned. If it's 2 dice, then one way you might set that up is numbers 1 through 6. If it's... Okay, that's the only example I really had. But not only can the columns and rows perhaps change, what you put in the cells might also change depending on what's being asked. So in this case, like 1A, it's probability rolling the same number twice. So under these circumstances, the number is what matters. And so in each of the little cells here, you'll have all the possible combinations. Now I've done it in row column, you can do it column row, it doesn't actually matter. You just want to see how many outcomes have the same number rolled. And you don't even necessarily have to fill out the full thing to quickly realize the pattern. You can see it's just along the diagonals. Filling these out isn't the end of the world, right? Even without thinking too hard, you're just adding 1 to any given number, moving to the right, moving down. From there, you can see it's just everything come along the diagonal, 6 out of 36 or 1 out of 6. If you're getting really good at these, you could probably just look at that and realize it simplifies pretty nicely. But here's a way to visualize it. Alternatively, if you cared about like the addition of numbers, in this case, which ones add up to be greater than 8, then instead of putting the combinations of numbers in there, it's probably a better idea to put the additions of those two numbers instead. So 1 and 1 make 2, 2 and 1 make 3. It'll be very quick to see that pattern. You can see it literally just add 1 to the left, add 1 to the right, add 1 down, and then just keep repeating that over and over again. So usually you don't have to think too hard. From there, numbers greater than 8, well, you just have a look which ones are greater than 8. And then from there, well, count them, divide by total. That's your final probability. That's multi-stage experiments. So if you have things that have multiple stages to them, this was 2 dice rolls, this was different orders on different days, anything that happens in a sequence, either tree diagrams or sample space tables can be useful tools to help you solve these. From there, we can use a bit of set notation along with Venn diagrams to also explain certain things. So the way union and intersection work is as you see here. Venn diagrams, you essentially just have 2 events, A and B. They may or may not intersect each other. The intersection is denoted by this N looking symbol. It's kind of an N. It's just the common elements between A and B. So this is both in A and in B at the same time. The union is denoted by this like U kind of symbol, and that's all the things included in both A and B. and the middle as well. Now, I personally used to find this equation weird that described the union of them both because it said you have to subtract the intersection. And personally, I thought, well, the union must therefore be this bit and not the intersection. The reason why the intersection is being subtracted here is because if you just add A and B together, this is what that would look like. Here's A, here's B. If you just imagine adding those two areas together, you get a double up on the intersection there. And so if you had the same confusion as me, the reason why we're subtracting that intersection is not because we kill the intersection, it's because we want to kill the double up of the intersection. Is it clear enough why that works? Cool. The other thing worth mentioning is the order of the terms. It doesn't actually matter if you say B then A or A then B. It's the same thing. If I said one line intersects another line, so y1 intersects y2, is the same thing as saying y2 intersects y1, mathematically and in English as well. It's the same thing. So the order in which these are written doesn't matter. So how do you actually identify union or intersection? Keyword or is pretty much always used for union. Keyword and, well, this one doesn't really have an and in it, but essentially if it's one thing or another, you're doing union. If it's one thing and another, you're doing intersection. So a pretty standard example of union would be like a standard deck of cards, probability of drawing an ace or a heart. The word or, again, implies union, and so union equation is probably the way to go here. So you write out the union equation for that particular set of circumstances. You need to find these three terms. Probability of ace. This requires you to understand the deck of cards. I don't know how popular those are nowadays. I'm hoping you guys know the suits and the possibilities for a deck of cards. If not, buy a deck of cards and figure it out, or play solitaire, I don't know, something like that. Anyway, probability of ace, going to have, is that a hand raise for a question, or?
Oh yeah, it's a question.
Yep.
So like, you know, for the deck of cards, how like there's 52 and like we need to know like how many like different types of cards there are?
Yeah.
Yeah, so like, is there anything else we need to know like that for like the exam?
Anything else? I mean, a lot of, like, I mean, a dice, yeah. How does a dice work? That was assumed knowledge.
Yeah.
There's going to be, a lot of it should be assumed knowledge, just like based on stuff you would see in your everyday. I think
Okay.
it's pretty rare for someone not to know what a dice is. Maybe a little bit harder to know a deck of cards. I don't know how popular decks of cards are nowadays.
But they wouldn't throw in something that like we've never like seen before.
No. If they throw in something crazy like, I don't know, the whatever came to mind for some reason was like a transistor for electronics, they're not going to say, I have these sets of transistors, figure out the probability of selecting. It's going to be whatever information you need will be in there. And if there is assumed knowledge, it should be popular enough to where people shouldn't be like, I don't know how many aces there are in a deck.
Oh, okay. All right.
Yeah, and you'll get a feel for that as you go through. The Cambridge book covers a lot of them. And so if you feel like there's something in the Cambridge book where it's like, oh, I don't actually know what that is in the real world, then that's probably your indicator to memorize that for the exam, just in case it comes up.
All right. Okay, thank you.
Yeah, no worries. But okay, so assuming you know how the suits of a deck of cards work, there's 4 aces in any given deck, so probability of ace is 4 out of 52. There's 4 suits in a deck, so you either memorize as 13 cards per suit, or you just do 52 divided by 4 divided by 52 to no, other way around, 52 divided by 4 to get the 13. That way, you know either 4 suits for a deck or 13 cards per suit. Then for the intersection, here's an example of intersection. The intersection of ace and heart. So that means we need a card that is both an ace and a heart, of which there's only one given thing. Deck of cards means you have a number and a suit. there's only one of any given intersection there. So 1 out of 52. You have all the probabilities, add and subtract. So the only challenging part will be finding any of these individual probabilities, and that'll be case to case. A typical example of an intersection question might be something like this. I know this is definitely done in like year 9, year 10, where it's like we have a survey conducted of a certain number of people and they'll have certain attributes that they're comparing. In this case, I've done like the weekend activities. It could be music and games. It could be recreation. It could be, whatever they want to compare. The fastest way to solve these kinds of things is through a Venn diagram. Typically, you'll get information that says, here's the total amount of people that was involved, and here's the information that tells you how they're split up. A lot of the times, it's easiest to work from the intersection outwards. So you go from the most specific information and then work your way outwards to the least specific information. So typically that means starting at the back of the question, which is this statement: of the 22 who went to the beach, 12 also went to the movies. So we know the total of beach should be 22 people, 12 of which belongs in the middle because they did beach and movies. So you're going to put your 12 there. The follow-up for that is, if this total has to add up to 22, then that means you're going to have 10 for beach specifically. Beach, but not movies. Then from there, you just sort of work your way up. So that was this statement fully covered. You've also got this statement here, which is 35 people went to either the beach or the movies. So again, keyword or there, that's a union. So 35 should be across the entire board here. So if we have 35 across the board, and this is summing up to 22, then the difference must therefore be in the M spot, but not in the B. So you're going to put the 13 there. Then lastly, work your way all the way up to the end, which was, well, I guess the beginning technically. 50 total people. You just want to make sure that you either add up to 50, or if you don't add up to 50, you put the remaining on the outside. These are people that didn't belong to either set. So in summary, you typically work backwards with the question. Work all the way at the end of it, get the most specific information, which is the intersection, and then work your way back up to the beginning. Clear enough on how to set up the diagram? Yep.
Yep.
Cool. Okay. Now that we actually have our little diagram, we can answer pretty much any question. So how many people went to the movies but not the beach? Well, that's going to be this spot here. Movies excluding the beach spot, so 13 people. If you needed a probability of people attending the beach, the movies rather, then you would do 13 divided by the total of 50. You do want to include this external. Yeah, so 13 divided by 50, that may or may not simplify. Pretty sure it doesn't. As far as intersection notation, this spot on the Venn diagram would be described as M intersection B naught, because it's what's in M and not in B. So just this bit here. That's about it. So union, you're always solving from the union equation. I think they call this the addition rule, which is weird because there's a subtraction in there as well. Intersections and unions can be written either way, back to front. To move on from here. Okay. Next up, probability tables. So we kind of mentioned a little bit as to where like a full sample space table might be helpful. Probability tables are a bit more specialized with how they work. These are best used for where two events are contrasted or compared to each other, which is kind of like you can convert. Essentially, the easiest way to think about this is you can convert any Venn diagram into a probability table or a two-way table. The way this one works is it's typically best for intersections, because all the information, as you can see in here, the vast majority of it is intersections between the two events. So the way it works is you're going to have two events, A and B, whatever they describe. In this case, it could be like movies and beach. And the way it works is every column and every row have to add up to give what's in the blue at the end. So these two things have to add up to give this, these two numbers have to add up to give this, and even the external as well. These two have to add up to give this. Basically, any horizontal or vertical addition needs to add up to give the thing on the end. So how you actually populate this is by understanding that everything in grey here is an intersection. So if this is event A and this is event B, then the joining of those two, so if I have the joining of those two, it's the A intersection B, or we could call it B intersection A, whatever you want to say. Same thing over here. Here's A dash, so this would be like not movies, maybe, and this would be beach. Intersection of those. Rinse, repeat. That's going to be everything in the middle. On the outside is just the probability of any of those events occurring. So at the end is probability of this, at the end of this is probability of that, and they all need to add up to 1 because all outcomes in a given scenario need to add up to 1. Okay. This is best used when the information you have are intersections. So in this case, we have 65% of people play sport, 71% choose cardio. So we're comparing sport and cardio. You would set up your table with S and C, and then the complements to those probabilities. The other piece of information that makes it probably better for a two-way table is that the information you're given is an intersection. And the thing you're trying to solve is also an intersection. Now, that's kind of like splitting hairs by saying, oh, if you see intersection, you should do two-way table. Realistically speaking, a Venn diagram works just as well. So if you have a preference between doing Venn diagrams or doing probability tables, just pick the one that you like working with best, realistically speaking. But if you want to be like super efficient, then yeah, if you can see a bunch of intersections in your wording, just use that. The real thing to watch out for is looking for two things that are contrasted. In this case, sport, cardio. In this case, it was movies, beach. This is where you would use these kinds of tactics. But okay, so start by filling out the table. The first thing we had was 65% of people playing sport, so the total of the sport column should be 0.65. 71% of people doing cardio, the total of the cardio row should be 0.71. From there, you had 53% of people doing both, so the intersection of doing both should be 0.53. As long as you have one thing in the grey and two things in the blue, or like basically three things that are separated between grey and blue, you are able to fill out the rest of the table through addition or subtraction. So essentially, if you wanted to find like this spot here, it means that 0.53 plus this needs to add together to give 0.71. So that's what I'm saying there. From there, you can do your rearranging, or you can literally just do 0.71 minus 0.53 off rip if you already know how this works. You don't have to formalize it like this. That's going to give you 0.18 in this spot. You could continue from there. You could say, okay, 0.53 plus something equals 0.65, figure out what that is. Then you have this, you have this. You could figure out, well, you could figure out this one by doing 1 minus 0.71. You could figure out this one by doing 1 minus 0.65. You can fill out the entire table. And if you're learning these to begin with, it might be recommended just to fill out the full table and see, does it all add up to 1? Because if it doesn't, you've made a mistake somewhere and you know to correct that. If you're more, if you already have a deep understanding of how it works, then yeah, you would just hone in on the one that you actually care about, which in this case is choose cardio but not sport. So this is the not sport column, this is the cardio column, so we wanted this one. That's what we cared about. So yeah, there's a few error checking things built in here to help you out if you're getting confused on how to fill out these tables. Worth mentioning, these questions can be very easily mistaken. Things that might appear as intersections are actually conditional probability. the thing to watch out for here is that if the probability figure that was given is dependent on another probability figure, then it's conditional probability, not an intersection. So in this case, this kind of looks like what we were describing earlier. We have two assembly motors, line A, line B, and we have faulty or not faulty. Unfortunately, the way it's described is actually conditional, in the sense that 5% of the motors on line A are faulty. You might think that's an intersection between line A and faulty, but fault is actually dependent on the motor that it came on, the production line that it came from. And so this is similar to a tree diagram, in the sense that you started on line A and you either came off of it as faulty or not faulty, which apparently I don't have a little picture of. So it would be like doing, you have line A, line B, and then you have faulty or not faulty. This is pretty tricky. It takes a lot of practice to recognize whether or not it's conditional or whether or not it's intersection. Is my explanation, at least in the beginning, clear enough as to whether or not it's conditional or intersection?
Yeah, yes.
Yeah, because this trips me up. If I haven't studied this for a little while, like, I don't know, let's say every year it comes around, I have to remind myself how this works. So just preparing you guys in advance that this is pretty tough. You have to do a lot of these before you can really sink it in.
Okay, all right.
But yeah, that's that pretty much. So we looked at a whole bunch of tactics as to how you can solve these kinds of probabilities. At the end of the day, these are just tools. Like, this is just ways of visualizing what's going on, tree diagrams, unions, probability tables. The bare bones fundamentals is simply, this is all just describing probability, and all these tools are just ways of visualizing what's going on better. Anything in there worth clarifying any further? And if not, what kind of topic do you want to finish off the remaining 7 minutes that we have exploring?
Maybe can we go through some questions?
Yeah, so we're going to do some questions for sure, but we covered a lot of stuff here. Which part probably needs the most clarification as far as questions go? I know stuff like this can be a bit tough. Stuff like this, I mean, like, if I were to say, like, what most people tend to struggle with, it might be stuff like this, but all of it's fairly similar. If we're not particularly fast either way, I'll just sort of pick out some.
All right.
Okay, let's just head all the way to the bottom, and we can do some of the chapter review stuff. Get a nice mix. Some of those are a bit chill. Yeah, let's start working out here. Now, I've noticed an issue, which is for me to do anything on camera, I need to swap screen shares. So this new setup is apparently not great. Cool. We'll work through it. So we've got 5 minutes anyway. Let's start from... Can we do this one? Yes, we can. Construct a probability table. Cool. So starting from question 10, we have probability of A is 0.6, probability of B is 0.5, A intersection B is 0.4. Sorry, A not intersection B is 0.4. What I can do from here is just copy that down on some notes. Now I'm going to do something. I'm going to click screen share on my other camera. Does that get rid of what you were just looking at?
Yeah, got rid of it.
Right, and you can only see this now. Interesting. Okay, that's fine. We'll just copy it down and work from here. So
right.
Probability A is 0.5. So you can see what I'm writing now?
Yeah.
Cool. Probability of, well, it would help if I'm looking at the right thing. 0.6. Probability of B was 0.5. And then the intersection probability A dash intersection B is 0.4. And we're trying to construct one of those tables. So I'll start drawing the framework out. You guys let me know how we, well, maybe, what do we put in these spots here? So if I call this like 1, 2, 3, 4, what will we put in those spots?
At 1 and 2, you could probably put like probability of A and then probability of A complements, and then like, it's the same thing for like probability of B. Like probability of B at 3 and then probability of B complements.
Yeah, precisely right. Yeah. So as long as you didn't mix them up, which is like AB and B dash A dash, that's all that really mattered there. So keep them on the same row and column. Okay, now, where are we going to put this? So, okay, that's a bit tough. Maybe we could start labeling some more spots. So if this is spot 1, 2, 3, 4, 5, 6, 7, 8, 9, where does this one go? 0.6.
Spot 7.
Spot 7, yeah. 0.6. Okay, where does probability B go?
Spot 3.
And A naught intersection B?
2.
Yeah, spot 2. So you got the A naught, which is this, the B naught, the B, which is that, so 0.4 goes there. The question that we actually had to solve was A intersection B dash. So where is PRA intersection B dash? How can we solve that? Or at least starting, what spot is that on the table?
Spot 4.
Spot 4. Yeah. So we need to try and figure out how to get there. There's no direct path to it immediately. We have to solve at least one thing before we can get there. What spot would be worth solving beforehand?
Probability of A intersection B.
Yep. So spot 1, and what's that going to be?
That's going to be just 0.1.
Yeah, 0.1. Reason why? 0.1 plus 0.4 gives 0.5. They have to add horizontally. Now spot 4 is open to us. 0.1 here, 0.6 here. What is our desired probability going to be?
0.5.
Yeah. 0.1 plus 0.5 is 0.6. And that's it. So depending on what one the question gives you will be how you make your way through the table. You could obviously just fill in everything and then get it by default. And so, either works. All right, more interesting question. How do we get, no, I just realized we get time. If you want, stick around, we can do the union just for fun. Otherwise, feel free to chill. How might we do the union?
The union, like, so we found out like probability of A and then probability of B. So like we just add 0.6 and 0.5, and then we subtract both of them from 0.1, which is a probability of A intersection B.
Yeah,
And
correct.
that value gives you your probability of A union B.
Perfect. Yeah, exactly right. So that's just the addition rule, or the union equation. Probability A plus probability of B minus the intersection. And in that case, we're just going to get a final probability of 1, which shouldn't always be the case. Should it? Hang on a minute. For two-way tables, no, it won't always be the case, because this could also be a Venn diagram, and any Venn diagram could be a two-way table. So yeah, it's just kind of lucky the union was 1 in this case. It's not always 1, because an equivalent Venn diagram for this one would be fully contained within here. Some of them have stuff on the outside here, which would mean still everything adds up to 1, but it just means that this must have been 0. Yeah, and it was, because here would be 0.4, here would be 0, and here would be 0.5. So the fact that you have this as 0 is why there was nothing on the outside here. This bit is this bit. Alright, I mean that's about it really. I know we didn't do many questions, it was a bit of a... Well, no, we did the trig thing at the beginning. Yeah, so as far as where to study these things, again, the stuff's all at the top here, for at least for Cambridge Unit 1 and 2. I realise I'm not screen sharing it, am I? It's at the, on each of the notes, you have at the top where you can study these things. I am going to overhaul these eventually, call it end of week maybe, with the Unit 3-4 stuff and the Jacaranda book as well. That way you can see more than just one spot to study them.
Wait, sorry. What are you gonna do again?
So can you see the screenshot that I have?
Yeah.
So these, instead of just saying Unit 1 and 2, I'll show you where to do it for the Unit 3-4 books, as well as the Jacaranda books.
Oh, okay. Alright.
I'll try to go through everything and do that. It's a lot, but I reckon I could get it done by end of week.
Alright, sure.
Alright, cool.